Hello everyone, welcome to another video. Today we're going to be solving a convolution problem. This is problem 78 for the corresponding chapter. The problem says, employ graphical convolution techniques to determine f star g. So there are two fairly simple functions. Let's plot them up. So we have a function f so let's define this as 2, 4, 6, 8. I think that's enough. Before solving anything, let's first make sure that we're understanding. So we have, let's say we have 5 here. Not going to be proportional, but that's fine. And let's make this one 5 and 2. So the first function, let's say it's f. It's 5 times the step function. So it's essentially going to be this function. This is f of t. And then for a g of t, then we have a composition of steps. So we have 2u of t. So that one, it's gonna be this. And then at t equals 2, then we have another step that's subtract 2. So at t equals 2, the second step is activated, and we go to 0. And then at t equals 4, another step is activated, and it adds 2. Perfect. And we go up by 2. And then at t equals 6, the step goes down, and we have the addition of this one. So essentially what we need to calculate here is the convolution of these two functions. I know that it's not that straightforward. Always you can go ahead and apply the definition, but in some cases it's easier just to follow the graphical representation of the graphical technique to calculate it. So just to have it by definition, to have it here, the definition of f star g, or f, that's the actual thing. It's defined by the integral from minus infinity to infinity of f of tau g of t minus tau d tau. That's the definition, right? And you know that based on what you have studied in class, the convolution is essentially the multiplication of those two signals, but in a moving window. It's kind of, let's see if I can make it happen here. If I take this function and I move it from the left to right, and at this instance the two functions are multiplicating each other, 2 times 5, and we get something. When it passes, we have 2 times 5 again, but we have a bigger window of pulse multiplication, so the integral is going to be larger. Actually, it's going to be double, right? It's going to be the integral of the multiplication of these two steps. So 2 times 5 times delta t, which is going to be, in this case, 20, the multiplication. And so on. That's the whole idea with the graphical description. So let's take it step by step. So let's think of, let's say at t equals 1. I think it's a good example. 1 second. What are we going to have for the integral? And by the way, this is kind of the point of doing this graphically, is that you can uh, plot these functions and see what's happening around that time. So okay, there we go. So what we are shifting actually in time is the function f. Sorry, the function g. So let's make it happen here. T equals 1, that means that we have something like this. T equals 1 second. And then so on, right? So this is going to be minus 1, this is going to be 1, this is going to be minus 3, this is going to be minus 5. So in the multiplication or in the integral, what we're taking is this value times this value around this time interval, right? That's what is happening. So the multiplication in this case is gonna give us, let's be very concise. So if we apply the definition, f of tau g of t equals 1, so 1 minus tau d tau in this case is going to give us 10, right? So it seems like the pulse is coming, is here, then at the next step is here, then at the next point is here, and so on. So what does it mean, this 10? That means that the multiplication of those two signals for t equals 1 is 10, right? It doesn't mean that the whole convolution is 10 for any time t, but it seems like that's what is happening for t equals 1. Now let's make another point here. At t equals 2 seconds, what are we going to have? I'm going to make this again. So again, we have this function f equals 5. And then we have the other one. And let's put it at t equals 2. So that means that we're going to have this function. First term is 0. We have this. We would have something like this, and the other pulse is coming here. Okay, so in this case, the multiplication of those two is going to consider this area, right? This area. Remember that there's going to be 0. This is going to be, this is going to be 2 and 4. 2 and 4, this is 0 and minus 2. That's a train of pulses, of 2 pulses actually. And in this case, the multiplication or the convolution for t equals 2, minus infinity to infinity, f of tau g of t equals 2, so that's going to be, wait a second, I'm not doing t equals 2 here. This should be t equals 4. Right, because we moved it much more than that. Yeah, t equals 4. Just to be consistent. D tau in this case is going to be the integral. F of t is going to be 5. G is going to be 2, right? And dt, now it's essentially when we have the pulse active, is going to be 2 seconds. So the overall convolution for t equals 4 seconds, it's going to be 20. Yes. 20. So t equals 4 is going to be 20. Okay. But you know that was the point of doing t equals 2, right? At t equals 2, we're going to have the whole pulse here. For t equals 1, we have the integral being 10. For t equals 2, we're going to have t equals 20. And for t equals 4, we still have 20 because we're not adding nothing to the convolution. We're multiplying 0 here, essentially, right? For this delta time. So when we, let's say here, overall, we have, and let me make a point clear here with the plot of the convolution. This is going to be f star g, and we have 1, 2, 3, 4, 5, 6, 7, and 8 time. So from 0 to 2, the function is increasing, right? From, let's say, this 10, 20, 30, 40, 50, 10, 20, 30, 40, 50. So at t equals 1, the convolution is this. At t equals 2, the convolution is this. At t equals 4, the convolution is this value, right? So we know that the behavior is going to be something like this, right? Then it's going to be constant. We're not adding anything to the convolution. From 2 to 4, we're not adding anything to the convolution. But later on, for t equals 5, then we're going to be adding this piece here because the g function moved. So we would have a similar behavior here for t equals 5, t equals 6. We're going to have the full thing. And then for t equals 8, we're going to have 0. I mean 0 addition. So it's going to be something like this. Right? And we can, and that's it. That's going to be the convolution. That's graphically. We can understand that because in this case, it's a multiplication of two pulses. Essentially, when the first pole passes, we increase linearly up to we get to this value. Then we have the 0 poles. We're not adding anything to the convolution. And then we add the last poles and we go up to 40 and then nothing else. It keeps going forever, right? We're not adding anything to the convolution integral. Mathematically, it can be expressed as, and this is going to be kind of an ugly thing, composed of many sections. So 10t, that's a slope, right? That's a slope at this point. Let me add it here. This slope is 10. This slope is 10 too. So we have 10t u of t until we get to t equals 2 when the slope is 0. So then minus the same function but displaced in time by 2 seconds, right? And then we have another ramp activated at t equals 4. So 10 t minus 4 u of t minus 4 and plus in this case negative, right, minus 10 minus 8 u of t minus 8. So at that point we don't have any more increase on the convolution. You can try out the manual approach using the definition straight away. It's kind of complicated, but you can get there. You can get there definitely, and you should get to this same result. Okay, hope it helps. Thank you.